My dear students from Iman University, today we're going to start a new topic that is called solutions. Now, solutions are a type of dosage form, liquid dosage form mainly or normally, that we encounter in pharmacy. When we say the term solutions, although solutions can be gas, solid, or liquid, here we are mainly focusing on liquid dosage forms. So, after we finish the solutions, what you are supposed to answer or to be able to do, inshallah, will be to define the various types of oral and topical liquid dosage forms in the form of solutions. You also need to compare and contrast liquid dosage forms in comparison to other oral dosage forms. For example, can you compare liquid to a tablet? For example, if a patient takes a solution or if a patient takes a tablet, is there any difference or not? Solubility is very important when we talk about solutions, and here we need to recognize and describe the factors that can increase or decrease the solubility of a given solute in a solvent. Also, you need to be able to evaluate and select the proper solvent. What is the right solvent for a certain solute and delivery system and purpose? For example, if I say this liquid is supposed to be given orally and it's used for a certain purpose, what should be the solvent? And the solute itself, sometimes the drug itself can be present in different forms or, let's say, in different salts, so you need to be able to do that. Let's come back to the term, solutions. Here in pharmacy, again, I have to say in pharmacy, okay? In pharmacy, we are talking about solids, liquids, and less frequently gases that are dissolved in a liquid solvent. So, that is what we mean in pharmacy. To define solutions, because again, solutions can be solid, liquid, or gases, but as I said, we are talking here about liquids. So, to define them as dosage forms, we say that these are liquid preparations containing one or more chemical substances, solutes, dissolved in a proper solvent or a mixture of mutually miscible solvents. Sometimes you have more than one solute, and you cannot put all of them in water. Some of them will dissolve in water, but some of them will not dissolve. So, I may need, for example, to add alcohol to this water in order to make all the solutes soluble. How do we classify solutions? If I ask you to classify solutions, then you have different ways of classifying them. You cannot say, solutions are so and so and so. You will say, according to use, we can classify them as oral, otic, ophthalmic, or topical. This is based on the route of administration or the route of application or the area where I am applying the solution. This is one way of classification. Another way is according to what the solution has, what is inside the solution. I'll give you some examples. For example, if I'm talking about water or aqueous preparations containing sugars, then in this case, you have what we call syrups, aqueous solutions containing sugars. We call them syrups. Now, if these preparations have alcohol, so they are sweet hydroalcoholic, sweet and contain alcohol, then we call them elixirs. But we need to pay attention. Sometimes syrups may contain a little amount of alcohol, even then we call them syrups, But usually, elixirs will contain alcohol and have some properties. We'll talk about them later in order for you to differentiate elixirs from syrups. Normally, syrups will not contain alcohol, but they may contain it, But for elixirs, they always contain alcohol, and they are sweetened preparations. Now, if I have aromatic materials, and when I say aromatic materials, I'm talking about materials that have aroma, that have smell. These materials, the nice smells, usually they have nice smells. If they are dissolved in an alcoholic vehicle, then we call them spirits. But if they are dissolved in water and usually saturate the water, then in that case, we call them aromatic waters. So, we can classify them according to the area or use, the area of application or use. We can classify them according to the composition, and we can classify them according to how we prepare them, for example, according to the method of preparation. I'll give you an example, extraction. Extraction is a way where the material gets macerated in a vehicle, and the result of that can be tinctures or fluid extracts. Now, you are required to Google and know what is the difference between tinctures and fluid extracts. Are they different or the same? But anyway, extraction is one method. If I want to prepare a solution that is sterile, and let me emphasize here, what do we mean by sterile? Sterile means complete absence of viable microorganisms and pyrogen-free. Both, and aseptic-free, not only sterile but pyrogen-free. These are materials that can cause elevation in temperature or shock, etc. So, in such cases, the solutions that we get, we may refer to them as parenterals or examples like injections. These injections are prepared so that they are sterile and pyrogen-free. These are the methods of preparation. Now, let's talk a little bit about solutions. First, if you compare, for example, solutions to a traditional solid dosage form like a tablet or capsule, which one would you expect to have the drug absorbed more quickly and provide an effect more quickly as well? Of course, you would expect that to happen with solutions. Drugs from solutions are expected to be absorbed more rapidly compared to suspensions or other solid dosage forms like capsules or tablets. Usually, in these solutions, you will find not only the vehicle and the drug, or the solvent and the dissolved drug, but frequently, you will see that there is a coloring agent, a flavoring agent, especially when we talk about oral administration. You will find a sweetening agent and maybe other materials to improve stability. Another thing you need to consider when you want to prepare a solution is that if you have more than one solute, you might need more than one solvent. You might need a solvent system to make sure that each solute dissolves in this system. So, you have to pay attention to individual solutes and whether each solute will be able to dissolve in the solvent or solvent system. Now, because solubility is a major factor for solutions, let's talk about solubility. But before we talk about solubility, we need to talk about the forces between molecules. In molecules, you have forces inside them and forces between them. The forces inside the molecules are called intramolecular forces, and the forces between molecules are called intermolecular forces. The intramolecular forces inside the molecules include covalent bonds, ionic bonds, and metallic bonds, which you already learned about in school. But what about the forces between molecules? Molecules are neutral entities, so is there a force between them? Yes, there are forces between them, and these forces will determine the state of the material, whether it is solid, liquid, or gas. These forces, although much weaker than intramolecular forces, are very important. They are the ones that cause the material to be in the form of a solid, liquid, or gas depending on temperature and pressure. For most organic compounds, such as drugs, you will find that most of them are present in the form of solids. Let's come back to intermolecular forces. Intermolecular forces include attractive forces and repulsive forces. Repulsive forces prevent two molecules from interpenetrating each other and destroying each other. Repulsive forces become the major forces if the molecules come very close to each other. There must be some distance between the molecules in order to have attractive forces. If the distance becomes less and these molecules get very, very close to each other, then the repulsive forces will dominate. Attractive forces, on the other hand, result in the material being in the form of a solid, liquid, or gas, and they are also responsible for solubility when you put one material in another. Let's have an idea about these intermolecular forces. One type of attractive force is called van der Waals forces, named after the scientist who discovered them. There are three types of van der Waals forces: dipole-dipole interactions, dipole-induced dipole interactions, and London dispersion forces. Dipole-dipole interactions occur between molecules that have permanent dipoles, such as HCl. These molecules have a positive and a negative side, and the positive side of one molecule is attracted to the negative side of another molecule. This is also referred to as Keesom forces or orientation forces. Another type of interaction is ion dipole forces. For example, when you dissolve sodium chloride, NaCl, in water, the positive side of water, near the hydrogen atoms, will attract the chloride ion, Cl. While the negative side of water, near the oxygen atom, will attract the sodium ion, Na. This is how NaCl dissolves in water. Although the ionic bond in NaCl is very strong, the dipole forces of water molecules surrounding the ions are able to overcome the ionic bond and separate the Na and Cl ions. The third type of interaction is hydrogen bonding, which is a very important type of bond that gives water its unique characteristics. Hydrogen bonding occurs when hydrogen is bonded to highly electronegative atoms like nitrogen, oxygen, or fluorine. For example, in water, H2O, the positive hydrogen atoms are attracted to the negative oxygen atoms of neighboring water molecules, forming hydrogen bonds. This specific type of attraction is referred to as hydrogen bonding. When we talk about solubility, we need to relate it to the solute, the solvent, and the temperature, usually at atmospheric pressure. Solubility indicates the maximum amount of solute that can be dissolved in a given volume of solvent. If you dissolve the maximum amount of solute in a solvent, the solution is called saturated. If you add more solute beyond this point, the excess solute will separate or precipitate because the solvent cannot dissolve any more of it. There are different ways to improve the solubility of a drug. One way is to use a solubilizing agent, such as a surfactant. Another way is to use a different salt form of the drug. For example, instead of using salicylic acid, you can use sodium salicylate, which is more water-soluble. Reducing the particle size of the solute can also improve solubility because it increases the surface area. Increasing the temperature can improve solubility for many solutes, especially if the dissolution process is endothermic. Agitation, such as stirring, can also help dissolve the solute faster. Altering the pH of the solution can improve solubility as well. For example, acidic drugs dissolve better in basic solutions, and basic drugs dissolve better in acidic solutions. Finally, you can use a cosolvent system, such as a mixture of water and alcohol, to improve solubility. The heat of solution is another important factor. If the heat of solution is positive, endothermic, increasing the temperature will improve solubility. If the heat of solution is negative, exothermic, decreasing the temperature will improve solubility. For example, when sodium hydroxide dissolves in water, it releases heat, making the solution exothermic. In such cases, cooling the solution can improve solubility. The United States Pharmacopoeia, USP, provides a table to describe solubility in terms of the amount of solvent required to dissolve 1 gram of solute. For example, if less than 1 milliliter of solvent is required, the solute is described as very soluble. If 1 to less than 10 milliliters is required, it is freely soluble. If 10 to less than 30 milliliters is required, it is soluble. If 30 to less than 100 milliliters is required, it is sparingly soluble. If 100 to less than 1000 milliliters is required, it is slightly soluble. If 1000 to less than 10,000 milliliters is required, it is very slightly soluble. If 10,000 milliliters or more is required, the solute is described as practically insoluble. For weak acids or weak bases, their salts are generally more water-soluble. For example, acetylsalicylic acid, aspirin, is less soluble than sodium salicylate. If you take the salt of a weak acid or weak base, the solubility in water will improve. This is because water is normally the best solvent we consider in pharmacy. Examples of weak basic drugs include atropine, codeine, morphine, diphenhydramine, and local anesthetics like cocaine and procaine. For weak acidic drugs, examples include phenobarbital, a sedative, and antibacterial drugs like sulfadiazine and sulfacetamide. The salts of these weak acids or bases dissolve better in water. There is also a principle called like dissolves like. This means that polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. For example, a permanent dipole will dissolve another dipole, while nonpolar solvents will dissolve nonpolar materials. This is important when considering solubility. Now, let's discuss some examples of solvents and their benefits in pharmaceutical preparations. These solvents are used in the preparation of topical and oral liquid formulations. One of the most commonly used solvents is ethyl alcohol, ethanol. Ethanol is considered the next most useful solvent in pharmacy after water. When mixed with water, the mixture is called a hydroalcoholic mixture, which can dissolve both water-soluble and alcohol-soluble substances. The concentration of alcohol USP ranges from 94.9% to 96% by volume, determined at 15.56 degrees Celsius. Dehydrated alcohol USP contains not less than 99.5% alcohol by volume and is used when no water is desired in the preparation. Alcohol is able to dissolve many water-insoluble ingredients, such as flavoring agents and volatile oils. It can also dissolve some preservatives that are not soluble in water. Alcohol itself has antimicrobial activity, and if its concentration is more than 10 to 12%, it can act as a preservative. However, alcohol is not desirable in medicines due to its pharmacological and toxic effects, as well as the potential for abuse. The FDA has recommendations for the use of alcohol in medicines based on age groups, which you should refer to in your textbook. Another solvent is diluted alcohol, which is prepared by mixing equal volumes of alcohol USP and purified water. The strength of diluted alcohol is about 49%, which is slightly higher than expected due to a phenomenon called contraction. You should refer to your textbook to understand why this happens. Diluted alcohol is used as a hydroalcoholic solvent in various pharmaceutical preparations. Rubbing alcohol is another type of alcohol used externally for disinfection. It contains 70% ethyl alcohol by volume and may include denaturants, perfumes, and stabilizers. Rubbing alcohol is used for disinfecting skin, soothing rubs, and as a vehicle for topical preparations. It should never be used orally. Glycerin, glycerol, is a hygroscopic liquid that is syrupy, viscous, clear, and has a sweet taste. It is miscible with both water and alcohol, making it a versatile solvent. Glycerin can be used as a solvent, stabilizer, and preservative. It is comparable to alcohol but has a higher viscosity, which can slow the dissolution of solutes. However, increasing the temperature can improve the dissolution process. Glycerin is used both internally and externally in pharmaceutical preparations. Isopropyl rubbing alcohol is similar to ethyl rubbing alcohol but contains isopropyl alcohol. It is available in concentrations of 70% or 91% and is used externally as a disinfectant, soothing rub, and vehicle for topical preparations. Propylene glycol is another solvent that is viscous and miscible with both water and alcohol. It has a slightly sweet taste and is comparable to glycerin. In many pharmaceutical formulations, propylene glycol is replacing glycerin due to their similarities. The most important solvent in pharmaceutical preparations is purified water. Purified water is used in the preparation of oral liquid formulations like syrups. Ordinary drinking water cannot be used in pharmaceutical preparations because it contains impurities. Drinking water has 0.1% total solids, while purified water has only 0.001% total solids. Purified water can be prepared by distillation, ion exchange treatment, reverse osmosis, or other methods. Among these, ion exchange treatment is preferred because it is cheaper, easier to operate, and easier to maintain. For parenteral preparations, purified water cannot be used. Instead, special types of water, such as water for injection, bacteriostatic water for injection, or sterile water for injection, are required. These types of water must meet stricter standards to ensure they are free from pyrogens and microorganisms. Conclusion of the lecture. This concludes the discussion on solutions, their classification, solubility, and the solvents used in pharmaceutical preparations. In the next lecture, we will continue with this topic and explore more details. Thank you, and Salam Alaikum.